Okay, so the last video, we want to solve Laplace's rectangle on a square, or a rectangle. So it's not just that we have non-zero boundary conditions on one boundary, but we have, u of x0 is equal to f1, f2, f3, and f4. So what we're saying then, if we kind of draw this, we're going from 0 to A and from 0 to B. Now, for y, so this part right here, this is for y is equal to 0, we're saying that the function is equal to f1 here. For this one, we're saying y is equal to b, and the function is equal to f2 here. For x is equal to 0, we're saying the function is f3 here, and the function is f4 here, and in the interior of the domain, its Laplacian is equal to 0. Okay, so the way that we're going to do this is we're going to break this into 4 different problems, each one with only one non-zero boundary condition. So we'll look at this one. The function will be equal to, let's say, f1 here, 0, 0, 0. The solution to this one we'll call u1. Over here, it'll be equal to 0 here, 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 but it'll be equal to f2 there. And the solution to this one we'll call u2. Next up is going to be equal to f3 here, and it will be equal to 0 here. And we'll call this u3. This is the one that I'm actually going to solve. You'll see what I mean by that in just a moment. F4 here, 0, 0, 0, and we're going to call this u4. Okay, so just to clarify, u1 is going to be the function that's harmonic in the interior of the disk. It's equal to f1 here, 0 there, 0 there, and 0 there. u2 is the function that's harmonic in the interior of the disk, that's equal, of the rectangle, that's equal to 0 there, 0 there, 0 there, and f2 there, and so on and so forth. And then the solution to the overall problem is just going to be the sum of these solutions. u1 plus u2 plus u3 plus u4. Okay, and how do we know this is a solution? Well, if I do the Laplacian over here, by the linearity of the Laplacian, it hits all of these terms over here, and each one of them are harmonic. So all of those individual terms are equal to 0, so they add to 0. And if I look at, say, as an example, evaluating u at f3, well, u1 along this boundary is equal to 0, u2 along this boundary is equal to 0, u3 along that boundary is equal to f3, and u4 along the left-hand boundary is equal to 0. So, for example, if I evaluate u on the left-hand line segment right here, is going to be equal to f3. And f1, f2, f3, f4 are all functions. Okay, so in other words, we know how to solve, the last example that we looked at, we solved problems like this, where it was, we had 0 conditions, excuse me, the last problem we looked at, we solved problems like this where on the boundary it was 0 at each boundary piece except for 1, and we know how to solve that. We solved it using method of separation of variables, and so that's what we do for this problem. We have to break it down into 4 pieces and solve each one independently. Now, that's very tedious, so I'm only going to solve this one and let you guys figure out how to do the other ones, but it's all going to be very similar. Okay, now one thing that we need to look at is it's going to be the y function that has the homogeneous boundary conditions. I know that if whatever x is, if y is equal to 0 or b, remember this is a and this is b, if y is equal to 0 or b, the solution is going to be equal to 0 there. So I'm going to do separation of variables. I'm going to have u of xy is equal to h of x, phi of y, and again I'm doing the phi of y instead of h of y because it's the y variable that we do the boundary value problem with, and we use phi for that. Plugging this into the PDE is going to give h double prime of x, phi of y plus h of x, phi double prime of y is equal to 0. Rearranging, we're going to get minus h double prime of x over h of x equals phi double prime of y over phi of y, and this is going to be equal to minus lambda. If I just look at the phi equation, we're going to have phi double prime is equal to minus lambda phi. And now the boundary conditions are going to be phi of 0 equals phi of b equals 0. Okay, now we've done problems like this before. It's very similar to what we did in the previous video, except we have a b instead of an a. And so we know that the eigenvalues, I'm going to write up here now, the eigenvalues are going to be k pi over the length of the interval, which in this case is b squared, and then phi k of x is going to be any non-zero multiple of sine of k pi, y, sine of k pi over b y. Okay, now if I look at the h equation, so if I forget about this, and I just look at the h equation, it's h double prime over h is equal to minus lambda, so I can take care of the minus signs like that, and then I'm going to have k pi over b squared, and then I can multiply both sides by h. Sorry if I was standing in the way as I was doing that. I still haven't somehow figured out how to do that on the board yet, in this room. If I'm not in this room, I can do it okay. Okay, so again, h double prime equals positive times h of x. So the general solution is going to be h of x, I'll write it here. The general solution is going to be h of x is equal to a e to the k pi over bx plus b e to the minus k pi over bx. And there's going to be a different one for every value, for every integer, so I'll just go ahead and index these. And now our solution is going to be a series of these solutions times these solutions. So those are going to be the product solutions. And that's what I'm going to write now. So u of xy is the sum k equals 1 to infinity ak e to the k pi over b x plus bk e to the minus k pi over bx times sine of k pi over by. Alright, now we want to determine what the ak's and bk's are, and we're going to use our conditions on the left hand line segment and the right hand line segment to do that. Okay, so what we're going to get if we plug in what we get if we plug in x is equal to a, we're going to have u of ay is equal to the sum k equals 1 to infinity ak e to the k pi over b a plus bk e to the minus k pi over b a sine of k pi over by. And this is equal to f3 of, this is equal to 0. Over here, it's equal to 0. This is an a, not a 0. Okay, well, if I have a sine series that's equal to 0, it means these coefficients have to be equal to 0. Okay, so in other words, we're going to have ak e to the k pi a over b equals minus bk e to the minus k pi a over b. Okay, and so don't forget about this minus sign here. We have bk. What is bk going to be equal to? Bk is going to be equal to minus ak times e. Okay, so I'm going to multiply this over. It's going to be e to the 2k pi a over b. Okay, so that's what bk is. And let me come up here and make these replacements. So I'm going to have AK. Okay, so now what am I going to get? I'm going to have E to the K pi over a Y. That's just, or sorry, X. And then now my BK, I have an AK, so I'm going to factor this out. So it's going to be a minus, and then this E to the 2K pi, sorry, I messed this up. This is over, that's over B, sorry, X, 2K pi, and now I'm going to have 2K pi, so 2K pi A over B, then E to the minus K pi over by, and then times the sine function. Okay, so I'm just replacing bk with this expression here. Okay, so there's a number of things that we can do here to try to make this look a little better. But they're all, so there's a number of things we can do. There's a number of things that we can do to make this look a little bit nicer. I'm going to erase this down here so that I can do some of those things. I guess it's all going to be kind of messy. So I've got AK times E to the K pi X over B minus E to the 2K pi A over B E to the minus K pi over by. Okay, so I can almost like combine this into one exponent to get something like a minus y, K pi over b times a minus y, but I have two here. So what I'm going to do is I'm going to multiply. I'm going to multiply the outside. I'm going to multiply and divide by one, or sorry, I'm going to multiply and divide by the same thing. So on the outside, I'm going to multiply by e to the k, e to the minus k pi a over b. So what do I have to do on the inside to make up for that? Well, I have to multiply that. I have to multiply by that. Sorry, I got it backwards. I'm going to multiply that, so I need to divide by that on the inside. So here it's going to be e to the minus k pi a over b. Okay, so minus sign there. But if I multiply this, if I divide this by that, I'm just subtracting off the k pi a over b, and so I get something like this. And so this, well, this is now going to be my new ak. I'm just going to keep calling this thing ak because this is a constant. So I can just absorb this into the ak. So this is ak, and we're going to get e. Okay, when I combine these things here, it's going to be e to the k pi over b x minus a minus e to the k pi over b, sorry, this is a y, this is an x, not a y, times a minus x, but I'm actually going to write it as minus x minus a. Okay, so now that is what I'm going to replace up here. And again, like before, you can write this now as hyperbolic sine of k pi over b x minus a. In fact, maybe I'll just do it, maybe to show you what I'm saying here. This is equal to ak. Okay, so if I divide this by 2 and multiply it by 2, now this is hyperbolic sine. So this is going to be, and again, the 2k is getting absorbed into the ak because it's just a constant. We haven't figured out what it is yet. So this is going to be equal to k pi over b times x minus a times the sine function. Okay, and the last thing that we need to do, so I'm going to erase this now, so pause and copy it if you need to. So the last thing that we need to do is figure out what the AKs are. Okay, and for that we're going to use the F3 condition. So I know that U of 0, y, okay, if I plug in 0 to x over here, we're going to have the sum k equals 1 to infinity, AK, hyperbolic sign, it's just going to be k minus k pi over b times a, if x is equal to 0, times sine of k pi over by. Okay, and this is equal to F3 of y. Okay, well now, what do I know? I know that this, the AK times the sine, is just going to be the Fourier, or the sine coefficient of F3 relative to these sine functions. So this, AK, times hyperbolic sine of minus k pi over BA. This is equal to 2 over b times the integral from 0 to b. I'm going to use z as the dummy variable, so this is sine k pi over b z dz. And so this is my solution where AK is given by this formula here. Okay, so if I just want to like replace everything finally, I'm going to have 2 over b, that's the length of the y part. So this is the integral from 0 to b, F3 of z, sine k pi over b z dz, divided by the hyperbolic signs, so times the hyperbolic sign from the solution, so times the hyperbolic sign of k pi over b x minus a divided by this hyperbolic sign of minus k pi over b a times sine of k pi over by. And so that is the solution to the U3. And then you're going to have similar solutions to all the other problems as well. And then like when you solve, let's see, this solution here, you're also going to have, it's also going to be natural to have hyperbolic signs in there as part of your solution. Okay, that's it for this video. I know that was long.